Okay, so let's start with Unit 2. We're going to be talking very simple atoms, molecules, ions. If you took chemistry before, you've probably seen these concepts before, okay? But let's go over very briefly atomic structure. This is what an atom kind of looks like. Easy way to think about it is in the nucleus, it contains protons and neutrons. So the atom is made out of 3 subatomic particles, protons, neutrons, and electrons. The nucleus, the middle part, contains protons and neutrons. Okay. Protons have a positive charge. Neutrons have no charge. They're neutral. And since it's positive and 0, the nucleus has a positive charge. Okay. And by positive, I mean like in a magnet or a battery, right? There's one side that's positive, one side that's negative. Okay, now the protons tell you what element the atom is going to be. Okay, so it kind of tells you the identity of the atom. Number of protons tells you what element it is. The neutron tells you what isotope it is. We'll talk about what isotopes are in a second. Okay, and then the last subatomic particle are electrons, and they basically fly around the nucleus. Now, a lot of times when we draw it, we're going to draw these nice little orbits that go around the nucleus. But in reality, the electrons kind of fly around like all crazy around the nucleus. We call that an electron cloud because it kind of looks like a cloud, right? But when we draw it, you'll usually be drawing these nice little orbits. In later units, I'll teach you how to draw the atoms more specifically. But for now, you just need to know those 3 things, okay? And the electrons tell you what the charge is, which we'll talk about in a second. All right, so let's move on. We're going to talk about a little bit of just notation, how chemists write down the symbols for the elements, okay? So I want you guys to take maybe about a minute or 2. I want you to copy this right here, this middle section with all the colors on it, because this is how chemists notate or communicate what type of atom they're talking about. And while you guys do that, I'm going to pass around a periodic table. This is my gift to you guys, my Merry Christmas gift and my back to school gift. So don't expect anything from me after this, but take a second to copy that down and I'll give you guys a periodic table. If you have your own, this is a second gift I can give you, but just hold on to one you have. Okay, so the way that chemists communicate what kind of atom they're talking about, they try to use 2 numbers and a symbol, okay? So let's start with the symbol because I think that's the easiest one. So the symbol is basically the symbol of the element, right? So if you see C, that's going to be carbon. If you're talking about another element like nitrogen, you just put N. If you do oxygen, it's O, et cetera, et cetera. That one's pretty simple, right? Okay, the second number they use is this bottom left corner. So if you ever see a number on the bottom left of the symbol, that's going to be the atomic number, okay? And the atomic number, super simply put, is just the number on top of the box for that element. It's already filled out. Here, thank you. No, thank you. Did you want to lecture with me? Okay, so if we're talking about carbon, the number on the bottom left will always be 6. If we're talking about silicon, the number on the bottom left will always be 14. Aluminum, 13. It's just the number on top of the box, okay? Now, the number on the top left is the one that I want to spend a little time on. This is called the mass number, and this is going to be the number of protons plus the number of neutrons, okay? And this number right here is going to tell you what isotope, okay, or what type of element it's going to be, okay? So the symbol and the bottom left number are pretty simple. It just comes from the periodic table. This number on the top is the one that we need to do a little bit of math for. And this number is always equal to protons plus neutrons, okay? All right, so before we do our first practice problem, any questions on any of that? This might be a review from your previous chem classes. Okay. So let's do a quick practice problem. I'm going to have you guys try it out. You guys can always work with the person next to you, so it doesn't have to be dead quiet. It's kind of awkward for me to just sit here and watch you guys write. But I want you guys to tell me how many protons, neutrons, and electrons are in this element right here. 197 Hg. Okay, so take about 2 minutes. You guys can use your phone calculators, or I encourage you guys to do that. You guys have about 2 minutes, and then we'll go over it together. Alrighty, guys, let's go over this first problem together. So let's start with protons. That's the easiest. So we have Hg. So we're going to go to the periodic table, and if we look up Hg, how many protons does Hg have? 80. Yeah, great. Super easy. It's just a number on the very top. Okay, so Hg, mercury, has 80 protons. Okay, so I'm just going to write that down. I'll do it here on the bottom. Got 80 protons. Let's do number of electrons, because that's the next easiest one. If we have 80 protons, how many electrons do we have? Yeah, 80, same number. Okay, and the clue is right here. Atomic number is number of protons or electrons. They're going to be equal to each other. All right, so the one that we need to do a little math for are the neutrons, but that's pretty simple. We have this number on the top left, 197. We know that's protons plus neutrons. So we know that 80 plus the number of neutrons is going to give you 197. Okay, so it's just a basic algebra problem, right? If instead of neutrons, if it's a math class, you can just think of this as x. You just find x by subtracting by 80 on both sides. Okay, that's going to give you your neutrons are equal to 117. Okay, so the number of neutrons that you have is 117. And that's it. Any questions? Hopefully not too bad. All right, now, before we move on, let's talk about another way that chemists write the name of an atom. So we have the symbol, right? We have this nice symbol right here. Another way they do it is they write out the full name. So let's start with Hg. So Hg is mercury, right? So another way to communicate this element is writing the full name, mercury, and then they put a dash, and then they put the mass number right here behind it, 197. So you might see this notation as well. AP Chem exam likes to use both. So if you ever see something like this, something dash and then a number right here, just know that this number right here is the protons plus the neutrons. Okay, that's it. And that's pretty much like 99% of the notations that you'll see for these elements. Okay. All right, so let's have you guys try one more problem on your own. This way, we'll use. Actually, no, we'll skip this problem. This one's the same thing. If you want, you guys can take a look at 2.2. It's pretty much the same thing that we did in 2.1, but I just kind of want to save time. Okay, let's move on to the next topic. It's called atomic weight. So if you guys take a look at the box on the periodic table, number on top is called the atomic number. It's protons. The symbol is the symbol. And then on the very bottom, you have this number, and we call that the atomic weight. Another way you guys might have heard this communicated in your other classes, I definitely teach it this way, but this is the molar mass, okay? Okay, and the molar mass basically tells you how much the atom weighs. Okay, now, atoms are super duper small, so we can't like put them on a scale to figure out how heavy they are. And just like how we use things like pounds, right? We use like 10 pounds, 5 kilograms, 13 ounces, right? To talk about weighing atoms, we use something called AMU. Okay, this is called atomic mass units. You guys don't need to memorize that. Just remember when you see AMU, it's talking about weighing out individual elements. Okay, so let's talk about the number at the very bottom. Now, if you guys notice, this number at the bottom is usually going to have some decimals following it, right? The atomic weight doesn't actually tell you exactly how much every element weighs, right? Because some elements might have different number of electrons, right? So they all have a different weight individually. However, this number right here at the very bottom, it tells you the average mass of the element based on their relative abundance. So basically, if we go out into nature and we look for all of the potassiums. Okay, the average weight that we're going to get from all the potassiums end up being this number at the very bottom. Okay, and the calculation for that is very easy. Okay, so here we're going to do an example with carbon. Okay, so it tells you that 98.93% of all carbons are going to be carbon-12, and 1.07% are carbon-13. So if you want to find the average mass of carbon, what we're going to do is we're going to set up this equation. I know it looks kind of complicated, but it's super simple. All you do is you take the percentage and you turn it into a decimal. Okay. And if you don't remember, I know it's been a long summer. In order to turn a percentage into a decimal, all you do is you divide by 100, or you just move the decimal point 2 times to the left. Okay, so 97.93 becomes 0.9893. Okay, and then you multiply that with the isotope number. So if it's carbon-12, it's going to be 12 AMU. So you just multiply those two numbers. And then you just add that to the product of the other isotope. So the carbon-13 is 1.07. So if we turn it into a decimal, it's 0.0107. And since it's carbon-13, you can ignore this part right here. This is just added on for the other isotopes. Okay, and then you multiply the two products, you add them together, and then you'll get your AMU. Okay. So that's how you find relative abundance. That's how you find the atomic mass of the element based on averages. So I know that might be a little complicated. It's a lot of math, super early in the morning. So we'll do 2.3 together, and then I'll have you guys try 2.4 with the person next to you. All right, so let's try 2.3 together. We'll go over step by step, and then I'll have you guys try 2.4 on your own, okay? So I'm going to scroll down just a little bit so you guys can see a little better. Okay, so let's try 2.3. So it tells you that naturally occurring chlorine is about 75% chlorine 35, and 24% chlorine 37. It wants you to find the atomic weight, the average, God bless you, of chlorine. Okay, so we're just going to do the same thing that we did in the example that we saw right here. We're going to take our percentage, and you're going to turn it into a decimal. So 75.78%, you just move the decimal 2 times to the left. That's going to give you 0.7578. Okay, we're going to multiply that with the isotope number, which is 35. So we just multiply that by 35. Okay, and we're going to add that to the product of the other isotope. So this one's 24.22%. So if you move the decimal twice to the left, that's going to be 0.2422. And then you multiply that with the number for the isotope, which is 37. Okay, so the equation is pretty simple. Just take the percentage, God bless you, turn it into a decimal, multiply that with the isotope number, and just add it to the other one. That gives you your answer. Okay, so let's see how good you guys are at doing order of operations. So I'll give you guys about a minute or so to finish copying that down. Try to plug it into your calculator. You can compare with the person next to you, and let's see what you guys get. All right, everyone get about 35.48? Yep, for sure. And that's it. Super simple. One thing I do want to mention, I talked about in the Unit 1 lecture that we didn't go over, but if you watch the video, for AP Chemistry, try to cut off the numbers after maybe like 2 decimals, and you should usually be fine. There's this thing called sig figs that has a bunch of rules and things like that. But in my experience, you don't really need to use sig figs. If you give about 2 or 3 numbers after a decimal, should be pretty safe from there. Okay. All right. Okay, let's see if you guys can try one last one of this on your own, and then we'll move on to the next topic. Work with the person next to you. I'll give you guys about 3-4 minutes to do 2.4. If you guys can't see that very well, you can look on your Chromebook, but that's silicon 28, 29, and 30, so kind of easy to remember. Take about 3 minutes. Try to finish that up on your own. Check with the person next to you, and then we'll go over it about 3 minutes or so. Alrighty, guys. Did everyone get about 28.11? If you got 28.1, that's fine as well, as long as you're close to that. So similar concept. All you have to do is, isotope, percentage. That's it. Put them together, you get 28.11. Okay, when we move on to the next topics, anyone have any questions? I know it's a lot of info to take in. Second day of school, so early in the morning. I don't know why they put AP Chem first period. I'll be honest, I'm having a hard time thinking about math right now too. And I have a genetic advantage when it comes to math. All right. Anyway, before we move on to the next topic, let's very clearly define what an isotope is, because I know it's probably been a year or more since you've taken chemistry. And I want you guys to have a clear definition of what an isotope is before we go on to the next topic. Okay. So let me pull this up real quick, and I'm going to type it out for you. If you guys want to write this down, you can. But if you kind of understand what an isotope is, you don't have to. Okay. But the easiest way to think about an isotope is there are different versions of the same element. Okay, isotopes are different versions of the same element. Okay. What makes them different, or they have the same number of protons, but what makes them different is they have the different number of neutrons. Okay, so in the center of the atom, the nucleus, they have the same protons, and that's why they're the same element, right? If you have the same number of protons, you always have the same element. Okay, but what makes them different is they have a different number of neutrons. Okay, and I know that might not seem like a big deal, but the different number of neutrons completely changes how the atom is going to, I guess, behave. And my favorite example is uranium. Uranium-235 is found in a lot of rocks. So if you go outside, you pick up a rock, there might be some uranium-235, okay? But uranium-238 is used for nuclear fuel because it's radioactive, and if you touch it, you'll die. And so only difference is 3 neutrons, right? 235 versus 238. There's just 3 neutrons in the nucleus additionally, and that makes a very big difference in how they behave. And that's why we talk about isotopes, because even though they're the same element, right? Uranium and uranium, the neutrons changes how they work. Okay, that's like the most extreme example. Most of them aren't that big of a difference. Okay, but that's what an isotope is. Okay, now what we're going to talk about next is this thing called mass spec. Okay, and mass spec, very simply put, is a way to separate isotopes. Also, spec stands for spectrometry, but I didn't want you guys to write that. And so we just call it mass spec. Okay, but it's a way to separate isotopes. Okay, let's talk about how a mass spec device works, okay? So let's say that we have this machine, okay? And this is our mass spec machine, okay? And how this works is we take some type of gaseous sample. Okay, so basically we have a bunch of isotopes in this gaseous sample. I'm going to draw it kind of like a cloud, maybe a fart. Okay, and what we do is we put the gaseous sample into the mass spec. And this is a very simplified version of it, But what the mass spec machine is going to do is it's going to separate the different isotopes. Okay, so let's say that we are working with carbon. Okay, since we looked at carbon earlier, what it's going to do is it's going to separate the carbon 12s from the carbon 13s, from the carbon 14s, et cetera, and it's going to spit them out, and it's going to tell you what the percentages are. Okay, it's going to tell you what percent of the sample was carbon 12, what percentage is carbon 13, what percentage is carbon 14, so on and so forth. If you guys take college chem, you probably will work with a mass spec machine. My favorite memory is when I asked the professor what would happen if I farted in it, and they told me that they actually ran fart samples through it, and it separates the different molecules in there. There's a bunch of nitrogen, oxygen, and the thing that makes it smell is sulfur. But it tells you all the different things that are in there. Any questions on how a mass spec machine works? They're not going to ask you how does it work. What they're going to ask now is about the graph that it makes. I'm going to show you guys what that graph looks like. Okay, but again, all it does, it just separates the isotopes and it tells you what percentage of each they have. Okay, and what the mass spec prints out is this. We love graphs, right? Love math. Okay. So it's going to produce a graph like this, and let me tell you guys how to read this graph. Okay, so on the x-axis, I don't know if you guys can see this right here. This way, it's going to be the mass number or the AMU. Okay, so it's going to tell you, is it carbon 12, carbon 13, carbon 14? In this case, we're working with selenium. So this is selenium 74, this pillar right here. This bar right here is going to be for selenium 76. This one is going to be for selenium 77, so on and so forth, 78, and 80. Okay, so that's the x-axis. It's basically telling you which isotopes you're working with. Okay, the y-axis, how tall these bars are, tells you the percentage. So what percentage of the sample was each isotope? So x-axis tells you what the different isotopes are, and then the y-axis tells you how much or the percentage you have of each. So you guys can probably see it on your Chromebook. I'm not going to have it out on the screen, but I want you guys on your notes to just write down real quick how many different isotopes are there in this sample based on this graph. How many different isotopes are there? Let's write it down. And then which one do you have the most of? Which one is the most abundant? Take a second, just copy that or write that down on your paper. So how many isotopes are there? What's the most abundant? We're doing 2.5. And then talk to the person next to you. Let's see if you guys got the same answer. If they're wrong, tell them why they're wrong. Explain it to them. We'll take about a minute to do that. And then we'll go over 2.5. And then we'll go over the next ones. Alrighty, guys, let's go over together. So can you guys show me with your fingers how many isotopes are there of selenium in this graph? Yeah, 5. And then you guys can know that very simply because there are 1, 2, 3, 4, 5 bars, right? That tells you how many isotopes there are. Good. Okay, so there are 5 isotopes. And this is for what number is this? 2.5. Okay, 2.5 also asks us which one is the most abundant. And then hopefully you guys are able to identify it's the tallest one, right? Because the relative abundance is going to be the greatest. So the way that we would write it is we would write that the most abundant one is selenium 80. So you can write the symbol like that. Or if you wanted to write the whole thing, selenium-80, that works as well, okay? But don't just put 80 because the AP graders will be like 80 what? So just make sure you label it. Selenium 80. All right, 2.6, and I kind of asked you guys to do this a little bit later, but it's going to ask you how many neutrons does the most abundant one have? So we're talking about selenium 80, right? So to find selenium 80's neutrons, it's pretty simple. All we have to do is go to the periodic table and subtract the protons. So if we go to the periodic table and we look up selenium, it's 34. Okay. So we just do 80 minus 34, and that's going to give you 46 neutrons. Okay, that's it. That's pretty much like 95% of what you'll see for isotopes and mass spec. Any questions before we move on to the last one before our break? I'm going to show you guys how to draw a mass spec graph. Easy peasy? Okay, that's great. I just want to let you guys know I'm very proud of you guys for signing up for AP Chem. I know it's a big decision, especially when you see first period. Because I'll be honest, I was really sad when I saw first period. So that's when I like to warm up for the day. Can't really do math this early, but props to you guys. Okay, let's draw a mass spec, and then we'll try. I'll go over one with you. I'll have you guys try one, and then we'll take our break after that. Okay, so we're gonna move down to 2.7 and 2.8. Okay, and we're gonna do 2.7 together, and I'll have you guys try 2.8 on your own. Okay. All right, so it's telling you to draw the mass spectra. Mass spectra is just the graph you get from a mass spec. So the thing that we just saw. And it wants you to draw the mass spectra for rubidium, okay, when there are only two naturally occurring isotopes. The two isotopes are 85 and 87, and then you have the percentages up there. Okay, so I'm going to show you guys how to draw that. It's very simple. We're going to start by just drawing the graph. Yeah. 2.7. Sorry, I'll cover up 2.8. My bad.
What are the sites?
Oh, sorry, I'll write it down. It's going to be rubidium 85 and then 87. Sorry, guys, it's really small. Yeah, that's why I recommend having them up on your Chromebook just so you guys can see and zoom in and whatnot. Okay, so 85 and 87. All right, the first thing you want to do when you have to draw mass spectra is obviously draw the graph, right? I'm sure you guys are used to this from your math class. You're going to draw a graph, and then we're going to label the graph. So on the x-axis, you're going to have the mass number, or I'm really lazy, so I just write AMU. And on the left side is the relative abundance, but again, I'm pretty lazy, so I just put percentage. Okay. All right, so what you want to do is first, let's start with the AMU. You just need to label the isotopes that you have on the x-axis. Now, you don't need to draw all of them if you don't have them. So we have 85 and 87. So let's just be efficient. We're going to write 85 and 87. And then just so that the AP grader is very clear what element we're talking about, we're going to write RB on the top, just so they know we're talking about rubidium. Okay, and then the last thing that we have to do is draw the bars. And you don't even need to draw real bars. You can just draw lines. The only thing that really matters, there's two things, is first you want to label the number next on the y-axis, and then you want the numbers, the bars, to kind of make sense in terms of height. So if you take a look at 27 and 72, it's about 1 to 3, right? More or less, maybe 1 to 2.5. So we just need to make sure that the lines are about that much. So we're going to draw the line for 85 like this. And we just want 87 to clearly be about, you know, more than that. So that's, sorry, so that 85 is 1/3 of 87, around there. And then as long as you label the percentages, so here we're going to label 27.8%, and then here we're going to label 72. Sorry, I switched those up, didn't I? Sorry, I told you this is too early. This is 72, my fault. I apologize. I hear the sign already. Okay, so here is going to be 27.8. And then this right here is going to be 72.2. Sorry, did I see a question, or were you just going to correct me? Okay. And that's it. That is your mass spec. Super easy, right? All right. Any questions on how to draw a mass spec? Once we do the last problem, we are not going to talk about isotopes pretty much for the rest of the semester or the year. Yeah, we don't do isotopes too much. It's just this. Okay, let's have you guys try 2.8 on your own. We'll go over it together, and then we will take our break that you very much deserve. Okay, so here we have 2.8. We're drawing the mass spectra of oxygen. I'll leave the RB one up there for you guys. We have oxygen 15, 16, 17, 18, and we have the percentages. So I'll give you guys about maybe 3 or 4 minutes to try that. You can compare with the person next to you. We'll go over it, and then we'll take our break. Okay, so we're going to do the mass spectra, and this time we have 4 different isotopes that we're working with. Okay, so the 4 isotopes we're working with are for oxygen. So same thing, we have the exact same graph, but we're just going to label different AMUs to start. Okay, so we have 15, we have 16, we have 17, and we have 18. Okay, now I'm going to show you guys another way that you guys can do the percentages, just so that you guys don't have to measure it super well. But let's start with 16 because it's the highest, so that's going to be 50, so we'll make that pretty high. And then just because it's going to be annoying to try to, line up the y-axis with the height of the bars, I've seen it done this way before as well. Some people just write the percentage on top of the bar. That way it's just very easy for you to do and for the grader to see. Okay, so 50%. You don't have to do it either way. Whatever works best for you, okay? We'll go to oxygen 15. This one's 5%, so let's just make it kind of short, just so that we don't have to measure it. Again, as long as it makes sense, it's okay. You don't have to be super precise, so don't pull out a ruler or anything. Okay, we have oxygen 17, which is 25%, which is half, right, of the 50. So something that's about half as high, 25%. And then for oxygen 18, it's 20%, so just a little shorter than the 17, and you should be fine. Again, it doesn't need to be super accurate, especially if you just label it like this, then there's no miscommunication. All right, and congrats, guys. That is the first topic for the year that you've completely learned, isotopes and mass spec. We will probably not talk about this very much, but it might show up on the AP test, which is why we're going over, okay? All right, so let's take a 10-minute break. You guys deserve it. If you need to go to the restroom, go to the restroom. You guys take a stretch break, whatever you want, and then we'll come back and start the next topic, okay? Okay, so we got atoms, which are the individual elements that you see on the periodic table. But as you guys know, chemistry is interesting when they start combining together, right, to form molecules. So atoms are the little pieces that make up molecules, which form when you put together atoms, okay? So we're going to take a look at these formulas because this is how we communicate what a molecule looks like. So here we have the molecule K3PO4. Okay, so let's try to refresh our memories a little bit. I will give you guys 1 minute, and I want you guys to just write down your paper. How many of each element do you have? Okay, you can just write the symbol. You don't need to write the full name unless you really want to. But take about a minute. I want you guys to write down on your notes 2.9 how many of each element are in this molecule. Thank you. Alrighty, guys. So hopefully this wasn't too bad. How many potassiums do we have? 3. How many phosphorus do we have? 1. Yeah, and then oxygen 4. Good. Yeah, so we got 3 Ks, we got 1 P, and we got 4 O's. Okay, just the number in the back describes the one in the front. If there's no number, we assume that it is 1. Okay, easy peasy. All right, let's do one that's a little bit trickier. I don't know. Let's see if you guys remember the parentheses, but let's take a look at this compound right here. You got parentheses NH4 and then a 2, and then you got SO4. So I'll give you guys about a minute. See if you guys can figure out that one. Double check with the person next to you, and then we'll go over that in about a minute and a half. 10. Okay, so if we take a look here, I'll just write down the elements first. We got nitrogen, got hydrogen, we got sulfur, and we got oxygen. So sulfur and oxygen are really easy. It's 1 and 4, okay? So the nitrogen and hydrogen are the ones we need to look out for. Now, if you ever have parentheses, all you have to do is take the number on the outside of the parentheses and multiply it by the number in the inside. So if you take a look inside, there's 1 nitrogen, right? So how many nitrogens do we have in total? 2, yeah, because 1 times 2 is 2. And then hydrogen, there's 4 times 2, which gives you 8. There you go. That's how you count the elements for the parentheses. Just multiply the inside by the number on the outside. Any questions on that? Easy peasy. Hopefully I'm not boring you guys with this. Okay, so we'll skip 2.11. If you really want to try it, you guys can do that for your own notes. But we're gonna move on to one last, I guess, two definitions. We're gonna come back to this later in the year. This will be kind of important, so I want you guys to just get familiar with it. Let me zoom in a little. Okay. But I want you guys to at least write down the names that we have here in bold. Okay, so there are two different types of formulas. Okay, the first one, and this is the one that we know very well, molecular formula. Okay, a molecular formula, it basically just tells you how many of each atom you have in a molecule. The stuff that we just looked at. Okay, and that's called a molecular formula. Okay, if you want to keep it simple, you can just write MF. Okay, just remember what it stands for. It's molecular formula, not that other thing. So molecular formula. But the one that you guys might not be that familiar with is called an empirical formula. And I'll talk about what empirical formula is. We'll abbreviate this EF. Okay, but empirical formulas give you the relative number. Yeah, another way to think about empirical formula is it tells you the ratio. Take a second to copy that down, and then we'll go over what that means in just a second. We have 10 minutes, right? Okay, so let's talk about the difference between molecular and empirical formula. So we have two examples right here. We'll start with this right here. Molecular formula, again, it tells you how many of each element it has. So it's the most accurate way of describing a molecule, because it tells you exactly how many of each you have. However, sometimes when we do labs and things like that, we're trying to figure out something's formula. We have to figure out the ratio first, and that's where the empirical formula comes in. So if you guys take a look, the molecular formula here is H2O2, right? So there's 2 hydrogens, 2 oxygen. Okay, but the ratio between the two is 1 to 1, right? Because there's 1 hydrogen for every oxygen, 2 for 2, 1 for 1. And that's why the empirical formula for this molecule is just going to be O. Okay, it's just HO. Okay, because if you divide the 2 by 2, you get 1, and 2 here is 1. Okay, a more complicated example is this right here, is C6H12O6, this glucose. If you guys take a look, in order to get to the empirical formula, what we did is we divided it by 6, and that gives you the ratio. So the way that you go from molecular to empirical is you just divide by the greatest common factor. And you guys probably remember that from math class, the greatest common factor. Whatever number, they can all be divided to get a whole number. Okay, any questions between molecular and empirical? We're not gonna touch on this too much. On your exam, I will have you guys convert between them. So if I give you a molecular formula, I'm gonna ask you what the empirical formula is. That's a little hint to problem on your test. But we get more into detail about this later in the year. All right, so it's the first day, so we will end a little bit early today. Congratulations, guys. I know that was rough. A lot of stuff today, but take a break, and then, yeah, this will be uploaded on Canvas. Just keep an eye out.